Many transducers have a change in resistance with a change in the physical quantity that we're interested in. So the resistance of a transducer could change with temperature, it could change with strain, it could change with position, etc. And to improve the accuracy and measurements of these transducers, they're often employed in a Wheatstone bridge or included as part of a Wheatstone bridge. We're going to look at the circuit analysis of a Wheatstone bridge, and here's the configuration. We have 4 resistors, R1 through R4, to which we apply a voltage E halfway across it, so from this node to this node. Now there's going to be some current, and the currents on the 2 sides are usually going to be different. But we know that the voltage drop across each side is the same. So E is equal to current IA times the sum of these resistances, and it's also the same as current IB times the sum of these resistances. And on the other diagonal, we're going to measure voltage, and that's E sub G. And we know that E sub G is the difference between this voltage here and this voltage here. So that's IA times R1 minus IB times R2. Now we can substitute in these values up here for IA and IB to get this expression for the voltage that we expect in terms of the resistances and the applied voltage E. We're going to rearrange this in order to see a little something about the measured voltage. So here we are just getting common denominator and canceling out those terms, and we end up with this. So this equivalent expression for E sub G. Now we will have some measuring device, so we can't just know E sub G without measuring it, and the measuring device is going to have some resistance, so there'll be a little current flowing through, and that's shown as I sub G. Now if I sub G is close to 0, then this expression is accurate for the voltage, EG. In order to balance the bridge, if we get EG as 0, then we can use this expression to see that this condition has to be met. So R1 times R3 has to be equal to the product of R2 and R4. And now whenever we power the bridge, again, we don't have some ideal voltage source. Say we're using a battery, then we'll have a battery voltage and a resistance in series. And so we're not going to be applying this entire voltage to the bridge. So that means that the magnitude of the measured voltage is going to be reduced. But if we're operating in a balanced case where EG is 0, then that doesn't really matter. So this doesn't have an effect for a balanced bridge. Strain gauges are often used in Wheatstone bridges. Those are transducers that change resistance with changes in strain, and the change in resistance is very small. And so a Wheatstone bridge is used to increase the sensitivity of the transducer. And we can use this to measure resistance in a balanced bridge. So say that this is an unknown resistance, so it's a transducer, and we want to measure Rx. One way we could do that is to have an adjustable resistor adjacent to that unknown resistor, and then R1 and R2 are resistors with known values. So we know these values to a high degree of certainty, and R3 is adjustable. So when we measure EG as 0, then that means that these products are equal, and so we can rearrange that to solve for our unknown resistance. Bridges can also be used to measure impedances for AC circuits. Here's an example where we want to find this inductance, and we can adjust the capacitance value until we have voltage that's 0, or we could use a different bridge circuit with an adjustable capacitance in order to measure the frequency. Here is an example of a Wheatstone bridge being used for a DC system. Say we have these values for R1, 2, and 3, and R4 we want to determine so that we will have a balanced bridge. Here's the expression for the resistances in the case of a balanced bridge, that is, EG is 0. And so let's just plug in these values for R1 through R3 in order to come up with R4. So R4 is equal to 121 times 122 divided by 118. If we had 125 ohms at R4, then EG would be 0. Now in another situation, say that we know R4 and we know the voltage E that we're applying. Now we want to determine what voltage we would read. So here again is the expression for the voltage that we measure in terms of the applied voltage E and the resistances. So say this is 100 ohms, or 100 volts and 122 ohms for E and R4 respectively. We'll get that EG is 100 times 121 over the sum of 121 and 122 minus 118 over the sum of 118 and 122. And we end up with 0.628 volts. So if this R4 is 122 instead of 125, we will measure 0.628 volts instead of 0 like we would in a balanced case.